Hello, calculus fans. Okay, so in this problem, what we're going to do is try to find all values of x at which the tangent line to the curve y equals tangent of x over 1 plus secant x is horizontal. So basically that means we need to compute a derivative and set that equal to 0. That's how we'll know when the tangent line is horizontal. So in order to compute a derivative of this thing, we're going to need to use the quotient rule. So let's do that now. Okay, so we're using the quotient rule. Low d high minus high d low, square the bottom, and away we go. Now here's where it's going to be important for us to just know these derivatives of all these trig functions. Like here we have the derivative of tangent. And remember in the last video we wrote down the derivatives of all 6 trig functions. And I mentioned that it's important for us to know these. So that way we can seamlessly work through a problem like this. So if you go back and look at that, or maybe you remember, the derivative of tangent is secant squared. And then over here, we're also going to need to know the derivative of secant. Now notice the derivative of 1, that just disappears, but the derivative of secant was secant times tangent. So let's go ahead and put those in. So you should be able to see here that the derivative of tangent is secant, and the derivative of the 1 plus secant x is secant x tangent x. Remember, the derivative of 1 just disappears. So here you can see that the derivative of the tangent is secant squared, and the derivative of 1 plus secant x is secant x tangent x. Also, you should see that the derivative of 1, this part here, just disappears. Let's try doing a little bit of simplification here, including distributing this piece, and we'll see what we get. So just a little cleanup, and we end up with secant squared x plus secant cubed x minus secant x tangent squared x all over 1 plus secant x quantity squared. The one thing that we should see in here is that there's a common factor of secant x everywhere in the numerator. So let's pull that out. So you should see there's the secant x that we've pulled out of everything. Okay, so now we're going to use a trig identity. So right here, there's a trig identity that we can use on secant x minus tangent x. And if you've never seen this before, you might not recognize to do this. But it turns out that secant squared x minus tangent squared x is 1. So here we've just replaced this piece here with 1. Now I'll show you in a moment how you know that secant squared x minus tangent squared x is equal to 1, and maybe even more important than that, how you should remember something like that. But for now, let's just keep going with this derivative calculation. So we're just simplifying the quantity here. We can actually cancel out one of the secant x plus 1's in here. So if we do that, then we end up with secant x over 1 plus secant x. Now let's talk a little bit about how we did this step where we converted secant squared x minus tangent squared into 1. So I'd like to talk about that. So it turns out that that step is actually just an alternate form of the Pythagorean identity. So what's the Pythagorean identity? That is the statement that sine squared x plus cosine squared x is equal to 1. This is the easy trig identity that everybody knows at this point. So what we're going to do is we're going to take that basic Pythagorean identity and we're going to divide everything by cosine squared x. Okay, so basically like this. So we've divided both sides by cosine squared x. Now we can simplify each piece. Like this piece is tangent squared. This piece is 1. How about this piece here? Well, 1 over cosine is secant, so the one that we have there is secant squared. So when we clean all that up, we get tangent squared x plus 1 is equal to secant squared x. Now actually, I think that this is a trig identity that you should recognize as being one of the 2 alternate forms of the Pythagorean identity. So once we have this, then we can manipulate it just a little bit by subtracting tangent from both sides, tangent squared. And we'll just get secant squared x minus tangent squared x is equal to 1. So now you might not remember this trig identity, but I do think it's worth remembering this, or at least remember the existence of that, as being an alternate form of the Pythagorean identity. Now obviously everybody has to remember this. And I've got to be perfectly honest, if you don't remember the Pythagorean identity at this stage, then you've got bigger fish to fry than worrying about all these derivatives. This is a really basic identity at this point. And I mentioned that this is one of the 3 trig identities I know. And to be fair, this is the one that you really just absolutely have to know in order to be able to get by. So at this point, we've explained this step going from here to here. How is it that we turned secant squared x minus tangent squared x equals 1? Now let's go back and think about the original problem, which was to figure out where the tangent line was horizontal. So essentially, we're going to take this expression, which was our derivative, and set it equal to 0. Okay, so where's the derivative 0? Well, that basically means we have to set the numerator equal to 0, but secant x is never equal to 0 because secant x is equal to 1 over cosine x. There's nothing you could possibly plug in for cosine of x that would make that equal to 0. Okay, so what's that mean? It means that there aren't any values of x where the tangent line is horizontal. Now, it said in the original question, find all values of x at which the tangent line is horizontal. Now, the reading of that question doesn't necessarily imply that there are some, so you can certainly get a problem like this where the answer is there isn't any. And that's exactly what happened here. That's all for now.